Hey everybody, welcome to day one of week 26 of our complex booklet. And today, as day one, we'll be doing pages 1, 5, 9, and 13. And so I'm on page 1 right now, and we can get started. So the first one is integrals of foundational functions. Shade the Riemann sums for the parent constant function y equals f of x equals x to the power of 0, which is equal to 1. Right, this makes sense. From x is equal to 0, that's your interval. From x is equal to 0, that's your starting point, to x is equal to 4. Label left, middle, and right. So when we talked about Riemann sums yesterday, we talked about like there's different ways to do the Riemann sum, remember? So it's over here on page chart 26, page 4. Okay, it's on the top of the page. It talks about Riemann sums, and it says Riemann sums divide or partition an area under the curve into rectangles. Remember, we drew a curve and we sliced it into small tiny slices, and then we calculated the length and the area of those little rectangles, and we came up with an approximate area. That is exactly what Riemann sum is all about. Now there are 4 methods for creating the rectangles based on how the height is calculated. The height may be equal to the function evaluated at the midpoint. So you can take the height at the midpoint, you can take the height at the left point or at the right point of the rectangle. In the case of the trapezoid, it's equivalent to the average of the left and right approximation methods. Okay, so there's 4 different types of methods: left rectangle approximation method, midpoint rectangle approximation method, right rectangle approximation method, and trapezoid approximation method. So these are the 4 methods. So what they mean by left is you can start like your curve can just be touching the left side of your rectangle. That's what they mean by left rectangle. If your curve touches the midpoint, so here see the curve is touching the midpoint of your rectangle, you can draw your rectangle in such a way that the curve touches either the left or the middle or the right. Okay, and in the case of trapezoid, they said it's equivalent to the average of the left and the right. So it's this plus this, okay, and divided by 2. So they say the midpoint approximation is the most accurate one. So out of all of these, this is the most accurate one of the Riemann sums. Okay, so just bear this in mind. And now look at the example that they've given here. So look at this. This is your left. If this is your curve, or this is your line that passes through, and you're calculating the sums of these squares here, I guess. So here now it's like you're starting at the left. Okay, your rectangle is touching the curve at the left. So how many partitions do you have? 1, 2, 3, 4 partitions, right? And then here your curve, or in this case your curve is straight. So this is not really a curve. Your line is kind of touching the middle of your squares, right? This is the midpoint, and then here it is your right. Okay, so they've already labeled it, so there's nothing much to label there. So let's see what they're asking us to do. Yeah, there's really not much to label, except I think they want you to kind of shade this one. So I'm going to go ahead and shade this part. Okay. Okay, estimate the area of the partitions for all 3 Riemann sums. So if I take an area of length times width here, it is 1 plus 1 plus 1 plus 1. So that's 4 ones, which is equal to 4. And here if I start at the midpoint, okay, this is 1, 2, 3, 4 again, which is 4. If we estimate the area from the right side is also 1, 2, 3, 4. Okay, so that's also 4. Okay, calculate the area of each partition for the left graph. Okay, for this graph, sum the areas for the left Riemann approximation. Okay, your f of x equals length, which equals 1. So remember they said y equals 1. So our f of x equals 1. Okay, so when x is 0, the length is 1. When x is 1, the length is also 1. What happens is, whatever your x is, it's going to become x to the power of 0. So whatever your x is, it's going to become, if your x is 100, it's going to be 100 to the power of 0, which is 1. So it doesn't matter what our x is here. 2, still our answer will be 1, because 2 to the power of 0 is 1. 3 to the power of 0 is 1, right? And our width, okay, our width is this, which is our delta x, right? This is our delta x. What is our change in x? It's just 1 unit from here to here, 1 unit from here to here, 1 unit from here to here, and 1 unit from here to here. So the common width is change in x, which is 1 unit. Okay.